Okay, so hi everyone. My name is Einar Høst. I'm excited to be here today to talk about something that I care deeply about, which is how we try to build reliable services where I work at NRK TV. And I'm going to focus mostly on the process that we try to use to do what I like to call strategic reliability work. So NRK TV is where I work, NRK being the public broadcaster in Norway. NRK TV is our TV streaming service. So if you're a Norwegian and you want to sort of use the internet in some way to watch NRK's programming, TV programming, using your browser or your smartphone or your smart TV or whatever, then you're going to use the service that I'm talking about today. It is, I like to think of it sort of like a serious software service in the sense that I don't have the exact numbers, but say something like you have 500,000 users consuming 500,000 hours of content from the service every day. So it has some real uptime demands in a sense, and it has some real load to it. And that's part of what makes it interesting to work on. So the agenda for today, first, I'd like to talk a little bit about what the service itself is, because you can't really start thinking about building a reliable service until you know what the service is going to be. And then I'd like to talk a little bit, dig a little bit deep into what reliability really means and how we can sort of turn this abstract notion into something concrete that we can work on and improve. And that's going to lead us towards a process of what I like to call reliability engineering, right? So more like a structured approach to improving reliability. Part of that process is going to include stress tests, and I'm going to talk a little bit about the tools and techniques that we use for our stress tests to verify sort of that the mechanisms that we put in place to improve reliability actually work. But there's also this idea that these tools that I'm going to mention, they are sort of like humble, simple tools. There are no magic tools that you can sort of use to sprinkle reliability on your service. So you're going to have to put them together in a reasonable way to get some results. Okay, so what is the service? Well, obviously then it's a TV streaming service, and I'm sure you're all familiar with some of those. And if you're Norwegians, presumably even NRK TV. Specifically, most people are familiar with the TV streaming app, right? Which is sort of the user-facing part of the service, or the public interface of the streaming service. Of course, there's going to be a lot of stuff happening that's sort of invisible as well. We could take just a quick look at it to make it concrete. Can you see this? You cannot see it. It doesn't actually work. Now, presumably. Hopefully this is going to work. Can you see it now? Yeah. Okay, so, well, it looks like, I guess, any TV streaming service, right? So you have your front page here, and then you have a bunch of offerings. This is like my content, presumably things that I've looked at, and then we have all kinds of basically ways to try to entice people. We have sports events, sort of live things, so it's a combination of on-demand content and live content, and you can also go and see actually sort of the regular linear programming is also available, so you can watch the channels themselves live in the service, and then obviously you're going to have some search stuff and things like that. Like it might, maybe I'm interested in the daily news, so I can watch that, like here. So that's a very quick look at the service. Now, hopefully we're back with the slides. Yes. And of course, fundamentally, that's a client-server architecture with a bunch of different clients and a bunch of servers as well. So we run this, the API in 2 data centers in Azure. And in a sense, when you're using a TV streaming app, you're playing the game of hunt the media manifest, because what the user really wants is to grab a media manifest and start streaming some content that they're interested in. So interacting with the app itself is sort of just a means to an end to get to that content, right? And I like to say for the petabytes, for the mass volume of data, what you're really going to interact with is a CDN, right? So we don't stream that from our servers. And that means that our API is, strictly speaking, an API for metadata, right? It's worth noting that this service almost exclusively reads, right? Almost just HTTP gets, which is quite nice for us because it's much easier to handle a lot of reads than a lot of writes. We do have some writes, some to report progress, how far you watched, so that you can pick it up later on if you want to do that. And we have to report analytics, how many people watched what kind of content. Traffic sometimes occurs in bursts. It's not evenly distributed. So if you have a big launch, that's sort of like a mini Black Friday for us. So if it's a very hit TV show that sort of launched all at once, then we're going to have a lot of traffic suddenly. The same goes for important sports events and stuff like that. But again, it helps a lot that we have mostly reads, so we can cache our way out of some of those problems. OK, so that was a quick look at the service. What is a reliable service then? How can we make something like this reliable? And then we have to almost get a little bit philosophical. What do we mean by reliable? Well, when people talk about reliability, they're often going to use words like robust and resilient. And those sound nice, and they presumably have something to do with reliability. But in a sense, we just postponed the problem. So I said, OK, what is reliability? Maybe it's these two other things. Now we have to define those. So what does it mean to be robust, and what does it mean to be resilient? Let's start with the first one. I think robustness is about sort of how tough it is, how rugged it is, how much stress it can take or how much abuse it can take before it goes down. And there's this episode of The Simpsons where Homer picks up boxing. And it turns out that he does surprisingly well. And it's not because he's a good fighter, but it's because he's a very robust fighter. He has this specific genetical condition where his brain is insulated by an extra layer of fluid. So his opponents can sort of wear themselves out trying to punch him down. And then when they're exhausted, he can sort of just push them over and he wins the fight. So not a good fighter, very robust fighter. Resiliency is related to robustness, but not quite the same. So it's more about bouncing back from failure. If you fail, you get back up. And also, it is about continuing to work even under bad conditions. If something fails, you can still deliver some kind of service. So in terms of boxing, that's more like getting back up from the canvas. It's more like Rocky Balboa than Homer Simpson. And there's this annoying song from the 90s that sort of captures this spirit of reliability well, I think. So you get back up, but there's also this property of just not giving up, even though things are getting bad, even though you're starting to experience failures. And I have to say, the NDC conference has proven remarkably resilient. It's kind of impressive that we're still here, even under these bad conditions, and carrying on with the conference. So that's pretty cool. It's a resilient conference. And it's important to note that this robustness and resilience is not about, they're not Booleans. It's not like either or you're robust. Am I robust, yes or no? It's not like that. It's not even about percentages. It's more like when we say that a service is robust, it means that we've verified that it's robust against certain kinds and amounts of stress. Right? And it implies also that if we want to build a robust service, we're going to have to specify what kinds and amounts of stress we're going to talk about. Similar for resiliency, it means that you're going to be resilient under certain kinds of bad conditions. Right? And it's up to us to specify then what those conditions are going to be. So they're non-functional requirements. They're not going to be generic. They're going to be specific and contextual. So it's going to depend, crucially, on the service that you're building. And it's important also that these non-functional requirements are real business requirements, right? So they're not purely technical considerations. They're business considerations. They're going to probably have to be backed up with some technical consideration, definitely going to have to be backed up with some technical solutions, but still, they're fundamentally business requirements. Now, unfortunately, it's going to be real hard to go to a quote-unquote business person and have them specify what that's going to mean. And you don't have a domain expert for that, and you don't sort of have a product owner that's going to tell you what that's going to be. Apart from some vague notion, it has to be good enough, right? It has to work. So it's typically left unspecified, and then it's sort of up to the developers, I guess, to figure out what that's going to mean. And unfortunately, since it's ill-specified, developers often tend to sort of meet it with this best effort kind of approach, right? Everyone is going to try their best to create something that works reasonably well under most conditions. And if there's something particular failing, they're going to, or some obvious problems, they're going to try to fix it. And that's sort of all well and good, but in a sense, it's also a given, right? Most developers do try their best to create something that's good. The problem is that best effort isn't automatically good enough, right? It doesn't automatically meet that bar. So sometimes, quite simply, good enough has to be really quite good, right? And it's not necessarily fall out of this ad hoc process of doing your best, right? So you might not be able to reach this good enough target through ad hoc measures alone. And I'd like to add a few words then about a mindset here. And the reason for that is I've noticed sort of a change in my own mindset since I've been caring more about reliability and thinking more about how we can create a good process to improve reliability over time, to sort of work deliberately to improve the reliability. And again, most developers, are good people. They are conscientious people. They try their best, and they want to do the right thing. But at the same time, I think we're all often stuck in sort of like a compile time mindset, right? We sit and work with the code, and we're preoccupied with the business logic, which sort of correspond to the functional requirements. Right? And you might have heard like thought leaders say stuff like the code is the truth, or the truth is in the code, or something like that. And many developers seem to believe that. But I have to ask, what kind of truth is that? What truth are we talking about? The truth about what? Is it going to be the truth about what happens in production? Because if it's not the truth about that, I'm not sure what kind of game we're playing, right? It should be about what happens in production. But if we're going to talk about what happens in production, you're also going to have to factor in the runtime environment, right? You have to know something about the environment that your code is going to execute in, otherwise you're not going to know what the code is going to do. And then you also have to know something about the resources available. You're going to have to know something about the state of external dependencies, how the dependencies work over time, and so forth. And the problem is that the runtime is a very dynamic place, right? And it's also partially out of your control. Like, it might be that your code is running on some node. That node might be running some other code as well. And how does that affect the execution of your code? It's not necessarily completely knowable, right? So there's something unpredictable about this runtime. That means that runtime behavior is not entirely analytical. And by that, I mean that you can't really sit down at your terminal and stare at the code and know exactly how things are going to work out. So any truth, to me at least, that doesn't factor in this environment is going to be a lie. So I think we should complement that compile time mindset with more like a runtime mindset, which factors in this unpredictability of the runtime. We cannot figure it all out in our heads. And that means we have to move towards sort of like a systems thinking perspective, where in addition to this analytical approach, we also think more like, okay, I have a hypothesis of how this is going to work in production. I don't really know for sure, and I'm going to run some experiments to validate that my hypothesis is correct. And on a personal note, I'm going to say that being on call for a service really does wonders for this runtime mindset. It's not that I didn't care about reliability before, But when you get called up if things don't work, you care in a more visceral way, in a more concrete way, right? So skin in the game really has, it really does matter, right? And I know that being on call is not for everyone, and it definitely should be well compensated, but it's my experience that it affects the way you think. And you really concretely value simplicity, not just over complexity, but simplicity over sophistication as well, right? You prefer things that have fewer parts. I recommend reading this paper by Richard Cook. It's called How Complex Systems Fail, because what we are building are complex systems. And you can also watch one of his talks. They're great as well. Okay, so that was sort of reliability in general, I guess. So what about reliability at NRK TV? And I think, now this is just me throwing out an unvalidated hypothesis, but I think often you see that improvements start with some kind of crisis. And our crisis was not like an acute crisis, but it was more like this growing realization that our best effort wasn't really producing a result that we could confidently state was good enough, right? Wasn't really producing, in a predictable manner, reliability at the level that we wanted. So how then can we improve beyond best effort? Well, first of all, we're going to have some mechanism to tell that we're either getting better or worse, right? And then we need to measure something. We need some kind of feedback. And I think it's fair to assume that, in a sense, engineering is the combination of best effort and feedback, right? So you have this feedback to guide you when you're trying to do something well. So the purpose here is to move from an ad hoc process when you're doing reliability work to something that's more strategic. So we started looking at what's called site reliability engineering that you might have heard of. There's this Google book. And we decided to start to define some service level objectives for some of our services. Not all of them at the same time, but just start exploring this, right? And then you have to choose some service level indicators, which are going to be the things that you're going to measure. And that typically includes stuff like error rate. Now, error rate sounds very simple, but it sort of presupposes that you at least define what an error is. And that might be more subtle than you might initially think, right? It's going to depend, again, on the service, exactly what an error is going to be. And similarly, we might want to measure latency or response time from an API, which is really important when there's an end user waiting at the other end, right? But again, you're going to have to decide what kind of distribution you're going to accept for this latency. That's going to be a choice. And for more like pipeline stuff, say for publication of new content or the distribution of new content, throughput might be something that you want to measure. Yes. And of course, so the idea is to start measuring some of those things that matter to us and to back up sort of our gut feelings with some numbers. But I have to add some important caveats when you start measuring things like this. And the obvious caveat is that metrics can be harmful. And they often are. They can be abused and misused. They can be used, in particular, by management to sort of evaluate the effort of the team. How well is the team doing? Well, are they meeting their SLOs? And are those SLOs ambitious? That's one kind of abuse. If management does that, what you're going to find is that the teams are going to start gaming the metric in some way. And that completely undermines the purpose of doing this. What we want is to have something that helps us have a healthy process of strategic improvement or structured improvement. So you really have to have some quite deep level of trust in the organization before trying this, right? And in particular, trust that goes across responsibilities and across roles, right? Not just trust between the developers, that's fine. Also have to have sort of trust between developers and management. So when we started doing that, it was a completely bottom-up, sort of autonomous initiative, right? So it was the developer teams themselves that started doing this. It was self-imposed by the team. It was defined by the team. It was owned by the team. And crucially, there are no rewards involved in meeting or not meet, or punishments in not meeting an SLO, right? That's not the purpose of an SLO at all. And we definitely don't want to encourage competition between teams in setting ambitious SLOs and then reaching those goals, because that means that you don't understand the purpose of setting an SLO in the first place, which is an SLO should not be, the goal of an SLO is not to be ambitious, but to be appropriate, right? It's going to be something that's reasonable for the problem that you're trying to solve. So it should be appropriate, and if you can get away with it, it's much better to set a lax SLO, right? Something that's easy to satisfy, because that's much cheaper than to satisfy a strict SLO, right? So investing in meeting a SLO that's set too strict, that's pure waste. There's no reason to do that. And we definitely don't want to turn these SLOs into some sort of vanity metric, something that the developers wear on their sleeve or something like that. It's not something to wear on your chest. Okay, so what are SLOs for? Those were sort of all the negatives, all the potential problems. Why do we want them again? So we want them to guide decisions, because a lot of the time we have sort of technical choices we have to make. It might be that you're wondering if you should say you're having a cloud service and you're wondering, should I choose the regular blob storage option or the premium one, right? And one thing you could do is, okay, I'm going to try the regular one, that's the cheapest one, and see if I can meet my SLO. If I do that, there's no reason to invest in the premium one. If you cannot, you can try the premium one. If that fails, then you're going to have to go back to the drawing board. Maybe you can't use this blob storage solution. Or maybe your SLO is set too strict. So. Another purpose of having these SLO is to help communicate. And that's going to help communicate about the team's priorities within the team, outside the team, and to management. So if the team is currently having problems reaching their SLOs, that means they're going to have to spend more time improving the reliability of the service at the cost of producing new features. And that's something that management understands, and that's at least been my experience. And you can use it, of course, to validate the improvements or the investments you make into improving the reliability of your service. Right? In fact, you can work out several different design alternatives and try them all, run some experiments, and see what causes the greatest improvement. Of course, you put it in place also to notice regressions. Right? So it might be that you're measuring your service level indicators, finding that you're not really consistently meeting your SLOs. And you notice that, okay, that's been going on now for 3 or 4 weeks. So what happened back then, right? It might be that you deployed some changes to your code that made everything slower, or it might be that something in your environment changed, but still you need to handle that in a sense, right? It might be that something out of your control changed, but then you're still going to have to sort of take the necessary measures. Okay. With this in mind, and understanding that these SLOs are there to guide the team's priorities and to highlight their challenges also, and not to assess sort of the quality of the work itself, how do you go about actually defining one of these SLOs? And my experience has been that this is actually quite uncomfortable. This is something that developers are not comfortable doing, including myself. So we tend to shy away from it. But I also like to think of it in the opposite way. So if it's uncomfortable, it means that we're onto something. We're doing something right? Because the value add is in overcoming that discomfort and producing something. So you have to force some decisions, and you have to make sort of your gut instincts about what matters for the reliability of your service concrete. So you can't really hand-wave your way out of that. So here's an attempt to do just that for some of our endpoints. This is going to be, again, now one of these. This is the linear channel playback API with three of the endpoints. So what we measure here, well, first of all, we set a goal of uptime of 99.95%, which is kind of ambitious. We also chosen, okay, we're going to measure the error rate. We just measure, or we just count the 500 errors. 400 errors are not a problem, sort of with the service itself. And we set quite ambitious goals because basically we never want the service to produce an error. Right? Should never do that. Should do something else. For latency, we choose to focus on the 99th percentile, which means that for each of these limits, 1 out of 100 requests is allowed to take longer, but the other 99 have to be within these boundaries. But you also notice when you start defining these things that you have to be very specific. So this is measured behind the gateway or the cache, and that means that it's not necessarily exactly the same experience that the end user is going to get. So this is just for that API. And we chose the measuring interval of 1 minute, which basically says that, okay, we count the number of errors within that minute. We measure the latency within that minute. We calculate the 99th percentile within that minute. And we also set some limits for the load. So we have to have a minimum load, otherwise that typically you have some longer latency because things are sort of cold. And also you're going to have some sort of breaking point, right? So we say, okay, up to 50,000 requests per minute. And we also don't really care that much about what happens during the night because, again, the traffic is going to be low. So we basically just count what happens when we have significant traffic. So here's very simply our process. You basically just started measuring things, these service level indicators, before choosing the objectives. So we know something about where we start. Then we chose some objectives, and that was kind of painful because it felt arbitrary, but it's also entirely necessary because you need some starting point before you can iterate, right? And basically, you look at the numbers you have, you scratch your chin a little bit, and then you choose something. Once you've chosen something, you can start observing it. Like, over time, are we meeting these objectives that we chose? And then, periodically, you will revise or invest. Basically means that, okay, if we're failing to meet our SLOs, is that because we set too strict SLO, or is it because we don't have the reliability that we want and we have to make some investments? And when you're sort of in that position, you can now start to iterate over that. And that's sort of the structured process that we want to use. Okay, so observation, how do we do that? Well, it's very easy these days to put up dashboards. This is application insights, which shows for one of these endpoints that I talked about, the latency, I think. Yep. It shows actually 3 of these percentiles, the 99th percentile, which is the one we have an SLO for. It also shows the 95th and the 50th, which gives you sort of a feel for how the API works. It's fine to have more service level indicators or more indicators in your dashboard in addition to the actual SLOs themselves. Then we have reports. You can't really stare at these dashboards all day. So one thing that several of our teams have done is to implement this sort of weekly SLO report that gets posted to a Slack channel every week. So here we sort of echo what the SLO is. We also calculated the downtime budget. So if you have an SLO at 99.95%, that means you have a downtime budget of 4 minutes per week. So it's okay to violate the SLO for 4 minutes per week. This week, it turns out, or for the example that I took, we had 1 minute of downtime due to latency. So we were violating this latency SLO for 1 minute. And that's our granularity because that's sort of the chunks that we measure. And we also note outside the SLO hours, basically during night we had an additional minute of downtime if the SLO were to apply during the night. Okay, so what about notifications? Initially, we were tempted to set up notifications as well. So should we set up alerts to sort of notify the team that we're having ongoing SLO violations? And we actually tried that, but it just produces a lot of noise. And alerts should mean that there is some action necessary, and it's not necessarily the case that you know what to do when you, okay, now we had some slow calls. What should we do about that? It's not that easy to know, and it's sort of, these SLOs are not health checks. We have health checks, we monitor those. That's not what the SLO is for, so we stopped doing that. OK, so now we have our SLOs in place. We have this process for monitoring and revising our SLOs and for making investments. Are we done with this work now? So are we reliable at this point? Well, of course not. Right? This is a starting point. Now we have feedback, and that means that the real work can begin. Right? So this is just to help us do the real work. And I'd like to talk a little bit about architecting for reliability as well. So we make a very coarse distinction between what we call red and green services in the TV streaming service. And at the high level, you can think of sort of the public-facing part of the TV streaming service again, partitioned into subdomains like this. And then nothing to us matters more than playback, because there is no, at the high level, there is no definition of uptime that doesn't include also the user can watch the actual content on their device. If they cannot do that, we're down, right? It doesn't help. Whereas sort of recommendations and personalization and stuff like that, those are nice to have. We want them in our service, but they don't sort of contribute to this major use case, right? So they're sort of optional. We don't care that deeply about that. And we have some things that fall sort of in the middle, which are the things that help you navigate and find the content that you want to watch. Right? You might have a need to have some variation of those working as well. But importantly then, we want to define separate SLOs for these different subdomains, right? Because they have different non-functional requirements. That's why we have these color codes in the first place. We want to put into place separate reliability measures, and for that we need to run them as independent services. Right? And that also gives us failure isolation, which is very nice and important because it enables a scenario of partial failure. Right? And that's a key enabler for this resiliency. Right? Because partial failure is potential partial success also. Right? It opens sort of the door for graceful degradation. Right? If something fails, it doesn't necessarily bring the whole service down. But of course, that's just theory at this point. Right? So if the API sets the stage for graceful degradation, that's fine. Doesn't really help if the client doesn't also support graceful degradation. So we need to do some sort of validation to make sure that that's the case. And one of the techniques that we use for that is what we call a broken proxy that we insert between the client and the server. So say our API is working just fine. So I just included the personalization and the playback features now. Everything is really OK, and everything then works on the client as well. Then we insert this broken proxy, and the purpose of that is to introduce some sort of noise, right? Some latency or some errors, some stuff like that. So to break things, right? So maybe we take out personalization. All those calls fail now. And the purpose of the test is to verify that, OK, that happens. The client application loses the personalization features, but you can still watch the content. What often happens if you don't do this validation is that you're going to not be able to do the playback either, right? And then you lose everything. So this, to me, is the core of resiliency. What about robustness? We talked about defining SLOs and meeting SLOs, but that's not really what that has nothing to do with Homer Simpson, right? It doesn't really tell us much about robustness. So in a sense, it's not that hard to meet your SLO on a sunny day, right? Because you defined your SLO presumably on a sunny day by observing how things worked. But not all days are sunny. So robustness is about meeting your SLO on a bad day, right? And that means meeting your SLO under some sort of stress. And to verify or to check the extent to which we can do that, we run experiments, typically then in our pre-production environment. And we do that as stress tests. And I'm just going to mention quickly some of the tools that we use for that. I'm sure there are plenty of other tools out there. We've just chosen some that work well for us. And again, these are not magical tools, but they're good, humble, honest tools that we use to create experiments. Basically, we'll use anything that helps us set up a useful experiment to run against our services. So for load testing, we use K6, which has been good for us. I mean, it's fairly easy to set up. You just define your stress test or your load test as a JavaScript file, and then K6 is going to produce whatever number or configured number you have for calls against your service. And then we use a resiliency library called Poly. That's not really for creating the stress test. It's more about for implementing reliability features. It gives you potential for implementing timeouts and retries, circuit breaker, and so forth. Some of those sort of resiliency patterns that you may have heard about. And in conjunction with Poly, we use a very nice library called Simi, which is a fault injection library. It uses sort of the same programming interface, which means it's nice and easy to use. So you can basically use this similar to the broken proxy. You can use it to throw errors, introduce latency, also mock out responses and stuff like that. It's quite flexible. And then we use Unleash, which is a feature toggling tool. And we use it in a sort of, well, we use it for regular feature toggling. We also use it in a slightly unconventional sense to turn this noise on and off, right? So we control basically the faults that we inject with Simi using feature toggles, right? We do run also a pure load test, which can be useful sort of to find the breaking point for your service, right? So you scale up the load as much as you can and then see when the service starts breaking down, right? And then you can verify your scalability by sort of, okay, we're going to scale up now, rerun the experiment and see if our breaking point is higher. That means our scalability is working as intended. Now you might wonder about autoscale. Can't you just set up autoscale and it's going to take care of all of this for you? Well, you could, and we do use autoscale, but you have to validate that that works as intended as well. You have to verify that it scales up when it should, and that it scales back down, right? So you have to run these experiments regardless. And it's also the case that autoscaling is reactive, right? So if you have a lot of traffic coming in, basically like a tsunami, then sort of scaling up is going to be too late, right? Because the traffic already hit you, so it might be okay to verify that you can manually scale up proactively as well, right? In front of a big launch or something like that. Okay, so we run load tests with introduced faults in addition to these pure load tests. This is now the robustness test, if you like. So we have to simulate failure, similar to the broken proxy again. Now, if you're going to simulate a failure, you're going to have to think a little bit about what is it that can fail. And what often fails and causes problems is some kind of dependency from your API. Right? It might be an HTTP call to some other resource or some other service, or it might be a database call, something like that. And the problem with failures in these cases is that often also leads to secondary failures, right? It might actually be more problematic than the primary failures. And the secondary failures that I'm talking about is that both HTTP calls and database connections involve things that are limited resources on the runtime environment, right? So if you have now some latency, it means that these resources are being used longer than they should. They're not being freed in a timely manner. And that means when you're having new requests, there are going to be no resources left for them, and those are going to fail as well. So it's important to think about not only what can fail, but also how long does it take to fail. And I think the assumption that we all often use or make is that failure is just as fast as success. And unfortunately, in reality, failure is often much, much slower than success, right? Because often it's going to be some sort of delay or timeout that's going to occur, and then the error hits you. Okay, so if we have failures, what are some strategies and remedies we can put in place? What should we do about the failures? And then we have these reliability patterns, and we use Poly to implement some of those. And that's going to be timeout. You can put a cap on the time you are willing to be waiting to get a resource, or you might set up a retry, perhaps with some exponential back off, right? So maybe you wait for 100 milliseconds, then for half a second, then for a second, something like that. But implementing a retry basically means that you're betting that this error is actually a transient error. It's not necessarily the case. It might be that you're just sort of badgering a service that's having some problems. And if your service is having a problem, maybe you want to put into place a circuit breaker, which means that, okay, I'm going to stop bothering this service for a while and then try again at some later point in time to sort of give the server a chance to get back up. Okay, so those are some patterns, but if you're going to choose between some of these patterns, we're going to have to ask some more questions. And a sort of a fundamental question, if you have a dependency, is, do we really need the result? Can we make without the dependency at all? Can we avoid making the call? And you have to consider, how badly do we need it? Probably you need it a little bit, otherwise it wouldn't be there at all. But in a sense, for us, the only result that we really need is this media manifest link, right, to the place at the content delivery network where you can start streaming data. Everything else is sort of optional. I mean, we want to have pretty pictures, we want to have nice titles, we want to have episode descriptions and so forth. But in the end user is not really going to care that much as long as they can press play and watch the content, right? And that's then going to matter a lot for the strategies that we're going to choose. So if we don't really need it like absolutely completely, we might do well with the default value, and then you can set a short timeout so you can satisfy actually quite strict response time SLO. Or you might be able to use the cache value, right? That way you avoid making a bunch of calls, and you free up resources and can protect against errors as well. So I'd like to talk a little bit about caching. I mean, I'm sure a lot of you do caching in some way, but it's also such an important technique that I have to talk a little bit about it. And in particular, I want to sort of talk about the virtues of a good old-fashioned HTTP cache, right? So it's basically, in my mind, caching for free. You can just take your existing API, slap an HTTP proxy in front of it, basically any proxy is going to do, and it takes a lot of load, right? It protects against a lot of failures. And your API doesn't even have to be aware that it's there, right? The only thing your API is going to have to do is to set a cache duration header, and then everything else works like magic. So that's almost like this sort of resiliency magic pixie dust. And it's also worth thinking about how can you design your responses or your data so that it supports cacheability to the greatest possible extent. And I'm going to mention a particular instance. There's something that we call or works Board's time expansion algorithm. That's named for one of my previous coworkers who was sort of an advocate for this approach. And it's not really an algorithm, it's a sort of jokey kind of name. It's more like, maybe you can call it time independence principle. And the thing is that we have some values in our API that are time dependent. In particular, we have time dependent titles. And now I'm going to try once more. Oh, you can see this now. This was Dagsrevyen, this is the daily news. And if you see up there, let's see if I can point at it. It says, okay, idag, which means today. And then yesterday's news says igår, which means, again, yesterday. But then it falls back to onsdag, which is Wednesday, and so on and so forth. And I think, you probably can't see it, but then a few days later, it switches to showing now the date, right? The purpose is to make it easy for the end user to choose what they want. So typically, if it's one of the recent news, they want to know if it's today's news or yesterday's news. But then later on, it's probably, oh, I want to see the news from the 20th of November, right? Because something particular happened on that day. So in this scenario, let's just go back here. Yes, so we have these time-dependent titles for news episodes. How often should a client refresh to see if one of those changes occurred? Basically, it happens at midnight every day, right? Then suddenly it switches from today to yesterday. How often should we refresh, and how should we cache it? And what Board's principle says is this is stupid. This is completely stupid, because first of all, titles change very rarely. The title logic basically never changes, and then only at midnight do the titles change, right? And it's also completely deterministic, right? We know exactly what titles should be, what the title should be at any given point in time, so we can just generate a table, right? That means we're going to generate these titles. So basically, you're going to say that, okay, today, the title is going to be idag. Tomorrow, it's going to be yesterday. And then for a few days, it's going to be Friday. And then if it falls out at, you're going to default to the actual date. And this is a little more data than sending the title, but at the same time, you sort of freed yourself completely, and the client is going to know the time anyway, so you can just choose the right title. The idea then is that these time-dependent titles no longer have any meaningful influence on cacheability. Might be that you still want to refresh them every so often, but that's not going to be due to these time-dependent titles. So I just wanted to mention that as a concrete example of how you might want to design to improve cacheability. OK, so if you have that a failure, what are you going to do? We've seen that we can employ timeouts and retries, and it seems we've also seen that what we should do depends on the problem we're solving, and depends on how badly we need the value in the first place. So basically, if you're going to choose a resiliency strategy, that means you have some sort of hypothesis of what errors are going to occur and what might help to fix those errors, right? And then what you want to do is run some experiment to validate that your assumption is correct. So I want to show you a concrete case. This is, again, this linear channel playback API that we looked at. We looked at the SLO for that. And first of all, why is this API important? Well, we know it's important because it's part of the playback API, and that's one of those red services, right? And it's also particularly important because as a public broadcaster, we also have an obligation to be able to reach the Norwegian public with crucial information in times of crisis. For instance, if the Prime Minister calls a press conference to tell about the new COVID restrictions, then the public must be able to go to our service and watch that press conference, right? So this is sort of an obligation that our service has. And, well, how do we do this? How do we verify that we can sort of meet our SLO for this important service? Well, we use this load test with the injected failures. So we're going to inject failure now with SIMI. I'm just going to show you real quick what that is going to look like. Let's see if I can. I'm going to have to find my pointer. Where's my pointer? Here's my pointer. OK, so Visual Studio. I'm sure you're all familiar. This is it possible to read it? Not really. Is it a little bit small? Is it OK? You can see it? Well, let's see. OK, like this. OK, so what we do, actually, is this is now our SIMI Chaos Channels Blob Policy Provider, which is a descriptive name, I hope. And what we do is we fetch a policy for latency and for faults. And yeah, you can see here, depending on that policy, we're going to check, OK, is the fault config enabled? And if it is, we're going to use the specified injection rate. And then we're going to throw what's known as a three-headed monkey exception, which is one of these, which chooses an insult at random. These are taken from the Monkey Island game. And one thing that's nice about having these insults is that you see them very clearly in the log, right? So you can see, OK, these are some of the things that we injected. And OK. So that's the fault config. Then we have a latency config as well. And if we look at that, we can take a look at the fault config. What we're actually doing is that we're using these unleash toggles, right? So if it says that, OK, if this feature toggle here, inject fault always is enabled, then you're going to have, OK, enabled fault, injection rate of 1, which means always, right? And then we have injection rates of 90%, 50%, and 20%, and even 5%, and then disabled. So we have sort of something to play with there. And say similarly for latency. For latency, we can control both the injection rate and the length of the latency, right? So anything from a few seconds to a minute. So that was injecting faults with SIMI. And we use then unleash to control that. So it might look something like this. Here we have some of these toggles. Here we've chosen was not a terrible rate. I guess we should have specified the percentage there. I think terrible is 90%. OK, so at a very high level, this API, the task of this API is quite simple because, OK, it's the linear channels. That's some sort of metadata about sort of the names and the streaming URL for each of our channels. That changes quite rarely. So we have the specification for that in a blob. And that blob can be updated sort of out of bands by another process, right? Because changes can happen. Sometimes channels do change names. When counties change names, some of our local channels are going to change. And then we sort of want to reflect these updates. So our original design, when we started working on this, was something like this. And this is what I like to think of as sort of like a straightforward best effort attempt, right? So you put, basically what the API is going to do is going to make an HTTP call to the blob. And when it gets a response, it's going to put it in the cache. And we cache it for, I think, 5 minutes or something like that. Not very long, but still long enough to basically handle most traffic. But of course, there's something a little bit subtle going on. Because, OK, what's going to happen when the cache expires, right? So we have a bunch of requests coming in. The cache item just expired. That means that we're going to have to go fetch that blob. That's going to take a little while. Maybe it take like 50 milliseconds or something like that. In that time, a lot of requests are going to get a cache miss. And all of those are going to fetch that blob, right? It doesn't really matter that much. I mean, the blob can probably handle the extra traffic. But it's interesting to know that that's what's going to happen. Maybe we get a couple of hundred cache misses and a couple of hundred simultaneous HTTP requests. And then what's going to happen, all of those are going to put that into the cache. And the last one is going to win. And then we cache it for 5 minutes. And then the process repeats. OK, so then we ran this experiment. And it was a harsh experiment. So basically what we did was said we were going to inject failures for always. We're going to have latency always, and that latency is going to last for a minute, which is sort of a brutal test to put the API through. So what happened was this. So we had this sort of like background load, and then at this point, we let the chaos monkeys loose. So now every call is going to take 60 seconds and then fail. And you might wonder, OK, why did the traffic drop so much? So this is K6 generating this traffic. Basically, it means that all the clients have to wait 60 seconds before trying again. So that takes us from 1,000 to about 15 or 20 requests, right? Because 1,000 divided by 60 makes it drop. At this point, everything is horrible. Actually, it's worth noting that this happens, I misplaced that. It happens 5 minutes before, right? Because for 5 minutes, we had the cache protecting us. But then we had problems. And then we decided to increase the load from K6. What happens then? Well, more problems produced. Everything is even worse. And we increase the load even some more. But then something interesting happens. We decided to, OK, let's make 10% of the requests succeed. And that point, actually, the cache saves us, right? Because one of those successful calls are going to put something in the cache, and then everyone is going to get served that result. So that's good. But still, it's not great. So how can we improve this design? So there are various ways you can improve this. So you had sort of a naive caching approach. What we ended up with was running a hosted service as sort of like a regular job inside of our ASP.NET Core application. This is going to now trigger every 5 minutes and go fetch that blob and update just a regular object reference for the data. The API just checks that, and that's all it does. So basically, no client is now on that sort of hot path that involves fetching this blob. Now, yes, you might wonder then, what's going to happen if I restart the service and this thing is broken, right? Because then it means that a hosted service is never going to be able to read the blob. So for that, we actually hard-coded the data for our primary channels inside the API as well. So we have something to work on, even if the blob is, for some reason, completely unavailable. We will be able to restart or redeploy our application, even if that's the case. So this is an experiment I ran on the service a few days ago, trying to reproduce the same scenario approximately. So at this point, I turned on the chaos monkeys. As you can see, not much happened. Right? So at this point, all the calls to fetch or update this, the result from this blob are going to fail, but it doesn't matter to any of the requests. But in this interval, I cranked up the volume for K6. That means we're producing successful requests at a larger rate, but nothing much else happens. And then sort of the chaos monkeys just give up. I turn it off. And it means that the experiment now has validated that this is actually working as intended. So the idea is to make these injected faults completely irrelevant to the calls or to processing the requests. So the only consequence really is that any changes to the blob, of course, will not be visible in the service. That's the only impact it has. So is this now a robust design? That's a trick question, isn't it? Because robustness isn't a Boolean, right? That's what we talked about. But it is very robust against sort of problems with downloading that blob. It's not completely robust against Azure going down, at least not two data centers of Azure going down at the same time. Should it be robust against Azure going down? It depends, right? Depends on, are we meeting our SLOs, even though we can't factor in that Azure can actually go down? That's going to depend now on how well Azure performs, isn't it? Okay, so this case study is a simple scenario. We started with it because it was kind of simple to verify. It was not that hard to find a good solution. Other scenarios might be much harder. And in particular, if you're dealing with writes, it's probably going to be much harder. And the trade-offs that you're going to have to make are going to be much more painful, right? And you might have to run more different kinds of experiments, right? And perhaps a varied set of experiments to verify that you have, okay, we're happy with this solution now. And your result is only going to be as good as the experiments, because my experience has been, even very simple resiliency mechanisms, they never work on the first attempt, right? You're going to put something in place, you think it's going to work and it's going to look good, and then you're going to find out, it doesn't really address the problem, right? It looks good in the code, but it doesn't actually work. So you have to verify that. There's kind of a fun thing. There's one of the product owners that asked one of our testers a crucial question is this going to work on Saturday, right? And his response was, I haven't been able to make it fail, right? Because he was running a lot of experiments, trying to make it fail, and they weren't successful, and that means that, okay, presumably it's going to work on Saturday. Okay, so to summarize then, we want reliability engineering that requires some sort of feedback to guide our decisions. The right mechanisms to use are going to be context dependent. It's going to depend on the problem you're trying to solve. It's good if you can exploit your concrete context to find good solutions. If you have a lot of reads, you're lucky. You should always validate whatever mechanisms you put in place. You need to run experiments, listen to the feedback. And then finally, I'm just going to say that earlier this week, there's a workshop by Robustness and Roger Martinsen that delves much more into sort of the technical aspects of doing this and how you can use your tools to cover a wide variety of scenarios. Of course, it's a little bit late to sign up for that workshop now. Hopefully, they're going to run it again. I recommend checking it out. In the meantime, you can check out Bionic Repo, which has some of the same, which has sort of a setup with some of the same things that we've been talking about introducing faults, running K6, using SIMI, using Poly to implement resiliency features, and so on and so forth. So I recommend checking that out. And with that, I think I'm done. Thank you.